Each year since its inception in 1959, the Alton E. Bailey Award has been presented to recognize outstanding research and the exceptional service in the field of lipids and associated products. The award is sponsored by Archer-Daniels-Midland Company. We are pleased to announce that the 2021 Alton E. Bailey Award will be presented to David Julian McClements in recognition of his pioneer science, nanotechnology, ultrasonic spectroscopy and digestion, and his application of fundamental scientific principles to the design of foods with improved quality, nutritional value, and shelf life. Dr. McClements is a distinguished professor in the Department of Food Science at the University of Massachusetts, an adjunct professor at Zhejiang Gongshang University, and a visiting professor at the School of Public Health at Harvard University. He received his PhD in food science at the University of Leeds, UK, and carried out postdoctoral research at the University of Leeds, University of California, and University College Cork in Ireland before joining the University of Massachusetts in 1994. His work has been recognized by numerous awards, including the AOCS Stephen S. Chang Award in 2010 and the Supelco AOCS Research Award in 2016. He has published 5 books and over 1,100 articles in scientific journals, as well as numerous book chapters. He is currently the most highly cited author in food science and agriculture. Current work in the McClements Lab is focused on encapsulation strategies for the delivery of bioactive components and the use of nanotechnology and structural design principles to improve the health and sustainability of processed foods. They are also working to develop next-generation plant-based foods such as plant-based milk, meat, and fish. We recognize David Julian McClements as a preeminent researcher and innovator. We also recognize him as an outstanding mentor and leader in our community, the guiding light for hundreds of students and young researchers who are now making an impact in AOCS and the world. Congratulations, Dr. McClements.
Welcome, everyone. Thank you for joining us for the AOCS 2021 Alton E. Bailey Award Lecture, Applications of Advanced Emulsion Technology in the Food Industry, a Review and Critical Evaluation. I am Eric Decker. I'm at the Department of Food Science at University of Massachusetts. And I'm delighted to introduce Dr. Julian McClements as the recipient of the 2021 Alton E. Bailey Award. The Bailey Award recognizes outstanding research contribution and exceptional service in the fields of fats, oil, lipids, and related disciplines. This award is sponsored by Archer-Daniels-Midland. So I had the pleasure of meeting Julian when he joined our department in 1994. We've been able to work together for now over 25 years. During this time, Julian has certainly shown himself to be probably the most prolific writer in food science and maybe agriculture, with publishing over 5 different books and 1,100 peer-reviewed publications. These writing accomplishments have propelled him to be the most highly cited author in agriculture in the world. And it's not just this writing that has made him so famous, but it's also the way he's accomplished and gotten to these goals. And I think one of the things that many people probably don't realize as much is Julian is really outstanding at putting together research teams and putting those teams to get extramural money so he can hire lots of graduate students. And he's an outstanding graduate mentor. which really has allowed him to produce the data that's been needed for these publications. So it's my pleasure to introduce Julian's talk, and thank you all for coming.
Great. Yeah, thank you very much, Eric, for a very kind introduction. And thank you to AOCS for giving me this prestigious award. And I have to recognize that this is not just from my contributions, this is really for all the contributions of the many students that I've worked with and collaborators over the past decades or so. I've been very lucky to work with lots of very sort of creative, hardworking and dedicated students and collaborators. So they should take some of the credit for this as well. So today I'm going to talk about how we can use advanced emulsion technology within the food industry to try and address some of the important problems that we're facing as a planet that are associated with the food supply. So, some of the big issues that are things like health and wellness. There is a big increase in a variety of different chronic diseases which have been related to our food supply. So things like obesity, diabetes, and certain forms of cancer. We may be able to use these advanced emulsion technologies to create food with reduced calories, or to control the digestibility of the macronutrients in food, or to enhance the bioavailability of some of the beneficial components in foods. We also have to make sure the food supply is safe, and we can use these emulsion technologies to create novel plant-based antimicrobial delivery systems, or to create active packaging materials to protect our foods. And there's also problems with the sustainability of the food supply. The global population is growing, and we're using more land and more water, and we're causing more environmental damage now than we ever have. So we want to try and switch to a more sort of healthy and sustainable food supply. So that could be trying to reduce waste, converting some waste materials into value-added ingredients, or to sort of create more plant-based foods. And again, emulsion technology can be used in all these different areas. But if we're trying to reformulate foods to address these things, we have to make sure that they look good and they taste good, and that consumers actually want to eat them. So we have to focus on the sensory attributes and the quality attributes of food as well. So all of these things are integrated, and emulsion technology can contribute to all of them. And I'll give you just a few examples from some of the work we've done over the past 10 years or so in this area. So we can address some of the problems I've just mentioned using conventional emulsion technology. So a conventional emulsion, and I'll focus on oil and water emulsions here, consists of oil droplets dispersed in water. But even with this very simple system, we have a lot of flexibility to try and design improved food products. We can vary the type of oils that we use. So they can have different polarities or densities or viscosities, and that affects the characteristics of the emulsion and its functional performance. We can use different particle sizes. We can go from small to large particles. We can have them more monodisperse or polydisperse. We can change the physical state of these particles, so we can have them solid or liquid or semi-solid, and that will change the way they behave. We can also engineer the interfacial characteristics. So for example, the electrical charge sign or density, so we can make them strongly charged or weakly charged, positive or negative. We can change the interfacial thickness from a few nanometers to tens of nanometers. We can change the interfacial chemistry. So for example, we could put antioxidants at the interface and have antioxidant emulsifiers, which will slow down oxidation reactions. Or we can change the way that the emulsion responds to environmental conditions. So things like pH or ionic strength or temperature. So these are all things that we can design into these emulsions. But if we're going to do this, we have to use existing food grade ingredients. So things like phospholipids, surfactants, phospholipids and proteins and their combinations. So we have some flexibility for changing interfacial characteristics and other properties, but this is quite limited. So this is where some of these advanced emulsion technologies come into play, and how we can extend the functionality of these to address the problems we're trying to solve. So this just gives you some examples of advanced emulsion technologies. There are other ones as well, but these are some of the ones we've worked with over the past decade or two. So we'll start off by looking at nanoemulsions. So what is a nanoemulsion and how is it different from a conventional emulsion? So in most respects, it's the physicochemical characteristics of a nanoemulsion are the same as an emulsion. It consists of two immiscible liquids with one dispersed in the other in the form of small particles. The only difference is that the droplets are smaller. So typically the diameter is taken to be less than about 200 nanometers in a nanoemulsion. And because of that decrease in droplet size, you get some novel functional properties. For example, you can make them transparent, or you can get very big high surface areas, which can change things like the digestibility of the emulsion. So we can create novel products. So for example, as I mentioned, when the particle size gets much smaller than the wavelength of light, we can make a transparent delivery system. So we may be able to incorporate it into some kind of functional beverage and put oil-soluble vitamins or nutraceuticals into this product without changing its optical properties. What we often find is as we make the droplets smaller and smaller, thereby the bioavailability of any encapsulated substances increases. And I'll show you some examples of that. Again, by making the droplets very smaller, we can reduce gravitational effects and we can increase Brownian motion effects, so we can make things with better creaming or sedimentation stability. So there's a number of sort of applications in the food industry where nanoemulsions may be better than conventional emulsions. So when we're making these nanoemulsions, we can make them using two different approaches, and both of these are currently used in the food industry. We can use high intensity methods or low intensity methods. High intensity methods are probably the most widely used, and these form very small droplets by applying intense mechanical forces which will deform and disrupt the oil droplets to make them smaller. In contrast, these low energy methods are based on the spontaneous formation of small emulsion droplets due to changes in the physicochemical characteristics of the system. And this is usually achieved by changing things like the temperature or the composition of the system. So to give you some examples of these low energy methods, this is one we've used widely in our lab, is the spontaneous emulsification method. You just mix oil and a surfactant together and you drip it into water and it spontaneously forms these tiny particles. So you can make a nanoemulsion. And there are other ways of doing it again, which are fairly simple. They just involve changing composition or temperature. This gives an example of some work we did a few years ago where we were trying to make optically transparent oil-soluble vitamins, so we could put them in drinks like this. And what you find if you use this spontaneous emulsification method is that the droplet size, and therefore the appearance of the emulsion or nanoemulsion, depends on the composition of the system. So you have to optimize the oil phase composition. So if you get about 80% vitamin E, in this case it's in MCT oil, you can get a clear, transparent nanoemulsion with a small droplet size. But you also have to optimize the surfactant to oil ratio. So you can see here, you have to get quite a high surfactant concentration in order to make these transparent nanoemulsions. So in contrast, you can make nanoemulsions using high energy methods. So these are things like sonication, a high pressure valve homogenizer, or a microfluidizer. So in my lab, we do a lot of work with microfluidizers where you make up a coarse emulsion using a blender, you force it through two very narrow pipes, and this smashes the droplets together and you get very small droplets formed. So this is a very efficient way of making nanoemulsions. And when you're using these high energy methods, you also have to optimize the system. So you have to optimize the homogenization conditions. So things like the type of homogenizer you use, the energy density, which is things like the intensity in the sonicator or the pressure in a microfluidizer, maybe the time or the number of passes. And then you have to optimize the emulsifier properties. So how much emulsifier you have, what type of emulsifier you have. And then you also have to optimize the bulk properties. So for example, the viscosity and the interfacial tension of the oil and water phases. And if you optimize all those conditions, you can make quite small droplets using these high energy methods. So you think like, one of the advantages of using a low energy method is you don't need any sophisticated homogenizer. you can just use, simple oil, water, and surfactant mixtures. You think, well, why do people not always use the low energy methods? Well, there's a number of reasons. One of them is you typically need a very high surfactant concentration. So typically you need to get to like a 1-to-1 ratio of surfactant to oil to make very small droplets. Whereas if you use a high energy method, you can use a much, much lower emulsifier concentration, so something like 1 in 10. And then the other reason is for the low energy methods, you're very restricted in the kind of surfactants and oils you can use. So typically you need small molecule surfactants like tweens, and you use something like MCT oil to make them, whereas you've got much more flexibility with these high energy methods. So now we'll look at some sort of applications of these nanoemulsions. So one of them we mentioned already is to make optically transparent beverages. Another one is to boost the bioavailability of hydrophobic substances. So this is things like omega-3 fatty acids, or oil-soluble vitamins like A, D, and E, or nutraceuticals like curcumin or carotenoids. So what you find is if you have like a conventional emulsion, you get a relatively slow digestion and slow release of the bioactive agents. With the nanoemulsion, you get a very rapid digestion and rapid release of the bioactive compounds. So this is some work we did recently. One of my students did, Shelley, in our lab. So she made up 3 different emulsions from soybean oil, and she had oil-soluble vitamins encapsulated in here. And she measured the free fatty acids release versus time in the simulated gastrointestinal tract. So this was simulating the small intestine region. So you can see if you have large droplets, they're digested quite slowly and they're not fully digested. So what can happen is some of the vitamins can stay inside the non-digested component. But if you have small droplets in nanoemulsions, like 150 nanometers, you get very rapid and complete digestion in a relatively short time. And that has important implications on the bioaccessibility of encapsulated components. So that's the amount that's actually available to be absorbed by the human body. So you can see that if you have a nanoemulsion, you have a much higher bioaccessibility, so nearly 80% in this case, compared to a conventional emulsion with very large droplets. So this might be something you would find in a mayonnaise or a salad dressing or something like that. So I think that, this really highlights the potential of increasing the healthiness of foods by boosting bioavailability of these components. But when you're designing these nanoemulsions, you also have to take into account the type of oil that you use to formulate them. So for example, this was some experiments we made nanoemulsions with the same droplet concentration, and the same emulsifier, and the only difference was the type of oil that we used. So we use medium chain triglycerides, so this could be coconut oil, and then we use 2 longer chain triglycerides like soybean oil and flaxseed oil. So we've got a lot of omega-3s in, this has got more monounsaturated. And you can see that you get a relatively low bioaccessibility for MCT, and that's because it forms mixed micelles in the small intestine that are too small to fit in the vitamin. Whereas if you have these longer chain triglycerides, the vitamin can actually fit in them and you get a higher bioaccessibility. So this highlights that particle size is important, but also the composition of the particles is important as well. And that shows you it fitting into the hydrophobic core of the mixed micelle. So the experiments I've mentioned so far were with an in vitro gastrointestinal model. But do they actually work in practice when we feed nanoemulsions to animals or humans? And there is some evidence that they do. So this is an experiment we did with some colleagues in nutrition department at UMass, where we fed these nanoemulsions to rodents. And in this case, we had vitamin D encapsulated in them. And again, you can see that you get a higher level of vitamin D into the body than you do with a nanoemulsion than a coarse emulsion. So again, this shows that this actually translates to real animal studies as well. So this could have effects because some people are deficient in vitamin D. So nanoemulsions, some of the advantages of them, they're fairly simple to prepare. You have a lot of flexibility for designing their functional characteristics. And you can make transparent products, you can increase bioavailability, and you can increase the physical stability of foods. One of the main disadvantages is because the particles are very small and have a large surface area, that you can get faster chemical reactions. So some components can chemically degrade faster, and you will only have a limit. You have a limit to control things like controlled release in the system, because things tend to get released very, very quickly. So now we'll look at a different kind of sort of advanced emulsion technology. So this is Pickering emulsions, which have been a hot topic for probably the last 5 or 10 years now. So how are Pickering emulsions different from conventional emulsions? So in a conventional emulsion, you normally use a molecular emulsifier in order to form the emulsion. But with Pickering emulsions, you use solid, or these could be solid or semi-solid particles rather than emulsifiers, or use them as emulsifiers. So you disperse these colloidal particles in water, and then you homogenize them with oil. And what happens is these colloidal particles go around the surface of the oil droplets, and you get like a shell of solid particles around them. So when you're formulating these products, you can only use certain types of colloidal particles, and that depends on their surface wettability. So you can get colloidal particles which are predominantly hydrophobic on the surface, and they tend to stick in the oil phase, or predominantly hydrophilic. So ideally, you've got to choose the right kind of colloidal particle for the right kind of application. So for example, if you're making oil and water emulsions, you want to use colloidal particles that are preferentially wetted by water and will protrude into the water phase, and therefore they'll generate strong repulsive interactions between the droplets. If you're trying to make a water in oil emulsion, you want the opposite. You want something that's predominantly hydrophobic, so it sticks out into the oil phase. And you can notice here that these colloidal particles can stabilize emulsions by forming a shell around them, but they can also form a three-dimensional network in the continuous phase around the droplets, which provides mechanical strength and stops the droplets from moving. So that can improve stability as well. So what kind of particles can we use to form Pickering emulsions? So traditionally, we used inorganic particles, so things like silica or titanium dioxide. More recently, there's been a big focus on using plant-based or animal-based organic nanoparticles for this purpose. And these could be proteins like thein or whey proteins, polysaccharides, protein polysaccharide complexes, or even biological particles like viruses or spores. So one of the big advantages of making Pickering emulsions is they're very, very stable to coalescence. They're typically much more stable than a conventional emulsifier. And there's two reasons for that. They generate a very strong, the particles stick to their surface very, very strongly, so it's very difficult to remove them. And then they generate a strong steric repulsion. And if they charge, they also generate a strong electrostatic repulsion. So just to give you an example, this is with some of my collaborators I worked with in China. They did some really nice studies looking at the freeze-thaw stability of these Pickering emulsions. So they made the Pickering emulsions and put them through 3 freeze-thaw cycles. And you can see that even after 3 cycles, the emulsions were still stable, and so it didn't break down. So this could be good for applications where you want an emulsion that's stable to freezing and thawing. So maybe something like a microwave meal. The other application you can use Pickering emulsions for, and some of the other technologies I've mentioned, is to slow down lipid digestion. So, our ancient ancestors lived in an environment where food was very scarce. And because of that, they developed a very efficient gastrointestinal tract that has lots of mechanical forces and acids and enzymes that can break down all the food that you eat. The problem with the modern world is we live in an environment where there's lots and lots of food available, and we have the same gastrointestinal tract through evolution. So what happens is if we eat processed foods, they tend to get broken down very, very rapidly in our gastrointestinal tract. And then that can cause metabolic problems. So in particular, it can lead to overeating. And one of the way it does that, if we have a food that's not very processed, it will be digested slowly in your small intestine. And you have some digestion products at the end of your ileum. And these will send a signal to your brain to say, I'm full, stop eating. But if you have a highly processed food that's digested very rapidly, most of the digestion products are absorbed in the beginning of the small intestine, and there's few left in the ileum. So you don't get the satiety signal. So then you tend to overeat. So potentially we can try and redesign foods to slow down digestion and therefore increase the satiety of foods to try and prevent overeating and obesity. So we did some work in my lab, but also with some collaborators in other labs, for example, in Harvard and in British Columbia, where we've looked at using these Pickering emulsions to try and control digestion. So we made up an oil and water emulsion, in this example, stabilized by nanochitin, and then we put it through a simulated mouth, stomach, and small intestine, and we measured the rate of lipid digestion. And you can see that if we compare it with a conventional emulsion stabilized by tween, which is a molecular emulsifier, you get very rapid digestion. When you have nanochitin, you get much slower digestion. You don't get full digestion. So you should get less calories and a slower release of the calories from this system. And that's because the nanochitin forms a protective shell around the lipids, which inhibits the ability of the lipase to get there. But also because these positively charged chitin particles can bind things like bile salts and enzymes, which can interfere with digestion as well. But one of the problems you could have is this could actually, because you get less digestion, it could actually interfere with vitamin bioaccessibility. So you have to be careful when you're using these kind of technologies. So Pickering emulsions have a certain set of food products and applications where they may be useful. So they may be useful if you're trying to sort of inhibit coalescence during long-term storage in products such as, like a mayonnaise or a salad dressing. They may be used to form like a shell around particles, which can control the release of encapsulated component, or they may be good for inhibiting digestion. So again, you have to find the niche of applications for each of these advanced technologies. So now we're going to look at a different kind of advanced emulsion technology. So in this case, this is called a high internal phase emulsions. So again, how are these different from conventional emulsions? So these are emulsions where you have a very, very high dispersed phase. So for example, in an oil and water emulsion, you have a very, very high oil concentration, whereas a water and oil emulsion, you have a very, very high water concentration. So this is typically, the oil concentration is a bit higher than what's called the close packing regime. So that's where the droplets are spherical and they can't pack any closer. So often, if the particles are big enough, they'll actually become non-spherical. You get this sort of polyhedral kind of shape. And you can make, say, an oil and water emulsion that's got an oil content, which can be as high as 90% or more, depending on how you formulate the system. So an example of sort of an oil and water emulsion, which meets this criteria, would be something like a mayonnaise. So often a conventional mayonnaise will have a very high oil concentration, but we can make all sorts of other products. And one of the advantages of this is you have a very high oil concentration. So maybe you can encapsulate lots of hydrophobic components here, and you can create novel sort of semi-solid textures using this kind of approach. And these are very simple to make up. You can use either a molecular emulsifier or a Pickering emulsifier. You can blend the water and oil together just using a simple high shear mixer, and you can form one of these hypes. And then the surface of these hypes will be coated by your emulsifier. So they tend to be sort of semi-solid emulsions because you all the droplets are jammed very closely together, so you have some mechanical strength. So I'll just give you some potential applications for these kind of emulsions. So one of the things we've used them for recently is to create plant-based adipose tissue analogs. So like in meat, you're trying to simulate if you're trying to use plant-based ingredients to simulate meat, you're trying to simulate the the lean tissue, but also the adipose tissue, so sort of this white tissue. So this is what a real adipose tissue looks like. It's got these fat cells. So you've got triglycerides packed inside and then a cell around them. And using hypes, you can make something very similar. You can create these oil droplets, which are surrounded by sort of proteins or polysaccharides, just trying to simulate the cell wall structure. So this shows a picture of sort of beef fat one of my students took. And this is some of the plant-based fat that she's managed to make out of sort of plant-based ingredients and using these hypes. So we're trying to match the characteristics of this to beef fat so you can match those desirable quality attributes that it brings. And this is some work done out of Cornell by Professor Abes Burad there. So he's doing lots of fantastic work on advanced emulsion technology. And this is some of the work he did where he developed like a low calorie spread, where he did the opposite. He made a water and oil emulsion. So it looks like a spread, but the vast majority of it's water. So you can get like an oily feel maybe in your mouth, but should be much healthier for you. So again, so these hypes have got a certain niche of applications. So things like reduced calorie products like margarine and butter, or maybe spreads for making plant-based adipose tissue, or for encapsulation of hydrophobic bioactives. And a lot of work's going on in this area now, trying to develop these kind of systems. Okay, so the next sort of group of advanced emulsion technologies we'll talk about are these sort of filled microgels. So these consist of biopolymer particles which have got emulsion droplets trapped inside them. And we can make these microgels using a variety of different methods. And the one that we use typically in my lab is one of these injection methods. So this is an instrument we have where you can put in like a biopolymer solution here, and then you can drip it into a cross-linking solution, and you can form these microgels. But there are also other ways like microfluidics with templating methods, controlled phase separation, like complex coactivation, or emulsion templating methods. And we've used a lot of these different methods in my lab to make microgels. And one of the nice things about microgels is you can really increase the functionality of emulsions because you can control so many different aspects of the microgel. So you can control what you load inside them. You can control the pore size by using different types of and amounts of polymers and different amounts and types of cross-linking agents. You can change the electrical characteristics. You can make them positive or negative or neutral. You can absorb things to their surface. You can change the surface characteristics. You can change the size of the microgels, and that changes their functionality. And you can also change the type of interactions that hold them together. For example, hydrogen bonding versus hydrophobic interactions versus electrostatic interactions. And that will determine the way that the microgels behave in different environments. Again, we've used lots of different applications for these, and I'll just give you an example. This is one where we were trying to stabilize omega-3 fatty acids. And what we did is we made 4 different systems which had exactly the same composition and were made from the same elements, but we changed the spatial distribution of the elements in the system. So the different elements that we had were a hydrogel bead, a nanoemulsion, so this was an omega-3 oil, and casein, which is a milk protein. So the nanoemulsions were the source of the omega-3 fatty acids, the casein was a natural antioxidant, and the hydrogel beads were used to encapsulate them. So in these systems, we either just had the hydrogel beads with nothing in them and the casein and the fat droplets outside, or we just encapsulated the casein and left the fat droplets outside, or we encapsulated both the fat droplets and the casein, or we encapsulate the fat droplets and left the casein outside. So as I said, they've got the same composition, the same elements, but just in different spatial distributions. By changing the structure of the system, this has a really profound influence on the stability of the system to oxidation. So this is measuring T-bars, which is a measurement of secondary reaction products from lipid oxidation as a function of time. And if we just compare the 2 extreme systems, if you encapsulate the casein inside here and the fat droplets outside, now the casein can't act as an antioxidant anymore. It's tied up inside the microgel. So now these omega-3 fatty acid droplets are oxidized very quickly, probably due to transition metals like iron in the aqueous phase. If we encapsulate the fat droplets inside the beads with the casein, so the antioxidant is close to the omega-3 fatty acids, then you get very good protection against lipid oxidation. So again, it highlights the efficacy of using these microgels for certain applications. The other thing we've done is use these microgels to control the gastrointestinal fate of bioactive components. So we often want to deliver bioactive components to the small intestine or colon, but they have to pass through the stomach. And the stomach's highly acidic and has lots of enzymes there that can break down the thing that we're trying to we're trying to deliver further down the gastrointestinal tract. So we're trying to develop microgels to protect things so they can pass through the stomach. So this is where we use this encapsulator, where we made these calcium alginate beads. So we put alginate here, and the thing we're trying to encapsulate, we dripped it into a calcium solution, and then you get a suspension of these very small microgels, which are typically about 100 to 200 micrometers big. And they would look something like this. You'd have the alginate form a three-dimensional biopolymer network. And one of the things that we did is we encapsulated things like enzymes or probiotics, but we also encapsulated an antacid. So this was something to try and control the pH inside the microgels when they're in the stomach. Because if you don't have an antacid there, the hydrogen ions can diffuse in here and make the internal environment acidic inside of here. And this would kill anything inside the microgel. So we're trying to keep the inside neutral, even though the outside is acidic. So we did that by comparing two different systems. We had one system where we put our bioactive agent in, which in this case was lipase, which is a digestive enzyme. And then in another case, we put antacid in there, which is magnesium hydroxide. And then we sort of prepared gels that had about the same dimensions. And then we put them through a simulated gastrointestinal tract. And we measured the change in pH inside these microgels using a fluorescence marker. So if we had no antacid, then the hydrogen ions diffuse into here very quickly in the stomach, and the pH decreases very rapidly. If we have our antacid here, the pH inside here stays pH 7 over time. And that's because the antacid dissolves when it comes into contact with protons and releases magnesium ions and water. So that sort of neutralizes pH. So we can keep this neutral pH inside the microgels and therefore protect bioactive components. So does this actually work? So we did some in vitro gastrointestinal experiments where we encapsulated the lipase, and you can see that we measured the activity of the lipase in the small intestine phase. So lipase normally converts triglycerides to free fatty acids, so we measured the free fatty acid release. If we had the antacid present and we protected the lipase, then you got rapid digestion in the small intestine. But if you didn't have the antacid present, the enzyme was denatured in the gastric phase and lost all its activity. So this might be important if you're trying to deliver enzymes in an active form, like things like lipase or lactase that certain people with diseases lack, to the small intestine. So we've also shown this for insulin as well. We can protect it through the stomach. And more recently, we've used the same approach for stabilizing probiotics. So we've encapsulated probiotics in these microgels, and we've put them just alginate plus antacid, alginate plus antacid plus a nanoemulsion to try and fill some of the pores up. And we can find that if we use the antacid and the nanoemulsion, we can greatly increase the stability of the encapsulated probiotics in the gastrointestinal tract. And the last application we've had, like I said before, is to try and control lipid digestion rate. So we said that if things get digested too quickly, that can cause problems. So we've been trying to prevent that. And we've used various approaches to try and do this. We've designed different microgels, we've coated them with dietary fibers, we've embedded microgels in microgels, and we've used mixed systems where some of them are encapsulated and some are not, to try and get a rapid digestion followed by a sustained digestion. And this is just one example where we've used that technology. If you have a non-encapsulated system, it gets digested very quickly. Once it's encapsulated, you can really slow down the rate of digestion. So this could be good if you're trying to deliver something to the colon, or you're trying to stop things being digested too quick in the gastrointestinal tract. So now we're going to look at another sort of advanced technology. This is called multi-layered emulsion. So this is where you make up an emulsion stabilized by one emulsifier, which has got a charge. Then you add an oppositely charged polymer, which forms 2 layers, and then another oppositely charged polymer that forms 3 layers. And then we can repeat this process over and over again. So we can form these nanolaminated coatings. And we've shown that using this technology, you can really improve the physicochemical characteristics of emulsions. So for example, you can improve their stability to things like pH and salt. So this is an example where we had a protein stabilized emulsion. So this is beta-lactoglobulin. and that tends to aggregate near its isoelectric point. But if you use this multi-layer technology and put an extra pectin layer on, you can stop it from aggregating because you increase the electrostatic and the steric repulsion between the droplets. So you don't get aggregation at intermediate pHs here, you get a much more stable system. So this might extend the range of proteins like animal proteins or plant proteins in foods. And we've used the same technology to improve the salt stability of emulsions. So again, by forming a multi-layer, you increase the steric and electrostatic repulsion between the droplets, and therefore you can make it stable over a wider range of salt concentrations. And similarly, we've used it to improve the freeze-thaw stability of foods. So this is where we coated emulsions with 1 layer, 2 layers, or 3 layers, and then we froze them, and then we melted them, froze them, melted them, and measured the stability. And you can see that if you put 3 layers around these droplets, you could make something that was really good freeze-thaw stability, which could be good in like microwave meals and things like that. We've also used the same technology to control the gastrointestinal fate of food. So in some cases, you want the layer to fall off and not affect digestibility. But in other cases, you want the outer layer to stay attached to the droplet surfaces and therefore slow down digestion. And by using different combinations of emulsifiers and biopolymers, we can control the digestion of these systems. Okay, so the last kind of advanced emulsion technology I'm going to talk about what call these clustered emulsions. So this is emulsions where we induce aggregation or heteroaggregation of the droplets. So in this example, we took 2 different types of emulsions, both stabilized by proteins, but at the pH we used, one of the proteins was negatively charged. So this was beta-lactoglobulin at pH 7, it's negatively charged. And the other was positively charged. So this is lactoferrin at pH 7. So you can see they have opposite charges at the same pH. When you mix them together, you can get different kinds of systems formed. So you can either get these colloidosomes formed, where you have central droplets surrounded by the other type of droplet, and these tend to be fairly low viscosity, or you can form these particle networks. And these particle networks have a very high viscosity. So this is where we mix the beta-lactoglobulin emulsion, which is negative. It's got a very low viscosity, it looks like milk. The lactoferrin emulsion, again, it's got very low viscosity, it looks like milk. But when we mix them together at about an equal ratio, you get a very high increase in viscosity. You can form like a paste-like or gel-like material that might be useful in something like a dressing, but you have a much, much lower fat content. So here, the total fat content is only 10%, and we can form something that's gel-like. So in just conclusion, I think there's been a lot of really interesting work carried out over the last sort of decade or so on extending the functionality of conventional emulsions by using all these advanced structural design principles. And that's led to things like nanoemulsions and Pickering emulsions and hypes and these other kinds of emulsions that may have specific applications in the food industry to improve the quality attributes of foods or to create novel functionality. But I think what we still need to do is make sure that we can do this economically using food grade ingredients and processing operations, and that we can that they're going to actually behave as we expect them to do in real food products, like during storage and processing and during application when consumers actually use them. So I think there's still a lot of interesting work to do in this area. So just to finish here, I'd like to thank all of the students and visiting scientists and postdocs who've worked in my lab over the years, and all my collaborators. Again, like I said, this award is mainly due to a lot of the work that they've done. And again, thank all the people who've sponsored the research in my lab. So thank you very much for listening, and I'm very happy to answer any questions.
Well, thanks very much, Julian. That was a very stimulating talk. There are a couple of questions that have come through in chat. If people have additional questions, please send those to chat and we'll try to get to them in the time we have left. So the first question, Julian, is about Pickering emulsions. And the person is wondering whether you've done work or anybody has done work using starches to form Pickering emulsions and how those type of Pickering emulsions behave.
Yeah, I think people have used starch. So I think they've taken starch particles and then partially disassembled them to make smaller nanoparticles. Because I think one of the things with Pickering emulsions is the colloidal particles you use have to be much smaller than the final oil droplet. So starch granules are typically quite big, like 2 to 20 micrometers big. So often you have to disassemble them first. But yeah, people have used starch for doing that.
The next question is really about how to design the emulsions so that it could get to different portions of the digestive system. So the exact question is, how does emulsion size impact the portal system restrictions in order to reach the ideal location? But I think this question could also be expanded to the colon as well, and how you could have different emulsion systems that would release in different places in the GI tract.
Yeah, so I think, for different applications, you want different kinds of emulsions. So some kind, you want them to break down in the mouth and release sort of flavor components. Sometimes it might be in the stomach or small intestine if you're trying to increase bioavailability. And sometimes you want to get into the colon. So I think if you want to increase bioavailability, you typically need them to be relatively small so that they get digested very quickly. And they have to be made from a digestible oil of the right type, so you get the right kind of mixed micelles formed. If you want to deliver them to the colon, then you want something that's probably made out of dietary fiber, but it has to be small enough to get through the pylorus sphincter, which is like a little hole in the beginning of the small intestine, so it can actually travel down there. So it has to be less than about 1 millimeter. Then if you want something in the mouth, you probably want it to be made out of starch or something that will disassemble under the pH conditions in the mouth. So I think there is a lot of design in order to do that, but then still keep it stable in the product.
Next question is, you have a lot of great insights in the freeze-thaw stability. How about heated systems like a cookie? So I guess it's really about the heat stability, and would there be applications where you want to have an emulsion that has better heat stability?
Yeah, so again, it depends, like, do you want the particles to be stable during heating, which I think is probably easier to do, or do you want to keep like a bioactive component stable during heating? So then you'd have to maybe co-encapsulate it with some kind of antioxidant or something like that. So I think so I think it's definitely possible. We've done some work in that area. And I think one of the things you find in this area is very application specific. You have to design the emulsion for the specific problem you're trying to solve.
Could you talk a little bit more about encapsulation of probiotics?
Yeah, so in that experiment, we would mix the probiotics with a alginate solution, and then with or without nanoemulsions and antacid, and then you would inject it into a calcium solution. And that would lead to the formation of particles which are about 100 to 200 micrometers big, using that particular method we use. There are other methods you could use as well.
So what does that do to their viability?
Yeah, so we measured the viability, and they seem to be okay, after doing those processes. You always lose some of them, but if you compare the encapsulated ones with the control, you got orders of magnitude more viable probiotics after encapsulation.
The next one is, I'd like to know if you have any results regarding the formation of protein corona in Pickering emulsions and the side effects.
We've done work with protein corona on nanoparticles, so like things like titanium dioxide nanoparticles. So, I mean, in any complex system where you have lots of different surface active components or charge components, the interfacial composition is going to change over time as different ingredients compete for the interface, and you get things like digestion products. So it's a really hot topic area that a lot of people are looking at the moment, because it does affect the gastrointestinal fate of the particles afterwards.
The next question is similar, and they're asking about Pickering emulsions with Janus particles, specifically those aspects regarding self-aggregation of these particles.
Yeah, I've never worked with Janus particles, so I'm not really sure how they behave. But yeah, I think it's going to be a competition between themselves, because they've both got hydrophobic patches, and then the surface of the Pickering emulsions. So it's going to depend on the relative strength of those interactions and the composition of the system.
What is the best way to stabilize water and oil emulsions for food applications?
I mean, the best way we found is using PGPR, which is a non-ionic surfactant, oil-soluble non-ionic surfactant with a low HLB number. I think there's a lot of people looking for sort of natural plant-based alternatives to that, but I think there's still, we haven't really identified one.
Is there any way to apply your findings to homemade food with regular ingredients?
I think if you were like a home cook, I think if you knew something about emulsion science, it would probably help you to, maybe formulate your more stable dressing or dressings with novel characteristics. So I think you can use that, any kind of food chemistry for that.
Can you please tell us about the sensorial properties of the last technology, which you mentioned can be used for dressings like mayonnaise and have much less concentration of oil?
Yeah, we never did any sensory experiments on that one, but I think it would be interesting to do it. I think one of the things about these systems is they're held together by electrostatic interactions. So when they go in your mouth, you're going to get a change in the salt concentration. So as you increase the salt concentration, these structures are going to break down. So that could be either beneficial or adverse to the sort of sensory perception. So it would definitely be interesting to look at.
So the next question is asking about just advanced emulsion types and such as the Pickering emulsion and how the surface coverage or encapsulation. So I guess they're asking this, is in these technologies, do you get coverage close to 100% or is it partial coverage of the surface?
So I think typically if you've got any hydrophobic groups, these are typically hydrophobic surfaces. So if you have any amphiphilic molecules, they will tend to get there and you'll get almost complete saturation. But it'll depend on how big the molecules are and how closely they can pack there and what the concentration is as well. So typically it's going to be very close to saturation.
What are your recommendations for future research in the field of colloidal properties of milk-based proteins?
Ooh, yeah, I don't know. I mean, I think what most people are doing now is like trying to find alternatives to milk-based proteins, so like plant-based alternatives. So yes, I'm not really sure. I mean, I suppose like doing controlled delivery systems in the gastrointestinal tract, reduced calorie products.
Is it possible to make emulsions using only natural biopolymers as stabilizers and slow the acid-stimulated quick release in the stomach without using antacid?
It's usually quite difficult because, like protons are very, very small ions. So they can really rapidly diffuse, into these things. There are other ways you could do it. I mean, maybe you could use a multiple emulsion or something like that. That would break down in the small intestine.
Okay, that's all the questions.
Excellent.
Thanks everybody for attending.
Yeah, it's been a real pleasure. And again, thank you very much to AOCS.